Hello. The purpose of this video is to explain structural floors. There is a video, and obviously you're watching it. So on your document, you can find a link to this video. Anyway, so floors are basically um, horizontal surface, and they are designed to carry the loads of your structure or your building. So there are two types of loads: live loads. These are loads that are moving, like people and cars. Dead loads are loads that are fixed primarily because of the roof and the weight of the walls or the floor itself. That's going to be considered dead load, things that do not move. So let's discuss first wood floors. And if you have wood floors, you have a floor on the ground floor and an upper floor. And wood floors, they basically are the same, except that for the first floor, it will be raised above the ground floor, and you would have the joist. These are called joists, right? And they sit on top a foundation, and that foundation could be a block wall, and the foundation sits on top of a footing. Okay, so to protect and preserve the heat and uh, inside the building in terms of winter, they would also insulate that. So the all these purple uh, colored are insulation. Okay, so because the floors on the first floor are sitting above foundation floor, there will be a crawl space underneath, and this crawl space is convenient to put and run your pipes and your ducts and your electrical. Okay, and that's very convenient because if there's something that went wrong, like a leak, then you could crawl under and fix it. Okay, so now because it is open to the ground floor, the crawl space needs to be vented because moisture and other vapors will leak into that space, and that has to be vented. Okay, now because moisture basically is water, it will tend to condense under the joist, and under the joist will typically see rot or molds. Okay, and sometimes if the ground is too uh, porous with water and moisture creeps in like crazy, it would pool and create this um, small pool of water, and that water will attract insects, and it will be an infestation inside that crawl space. So nowadays, what they do is they put like a plastic vapor barrier over the whole thing, and they seal that on the sides of the walls around 24 inches above, so that you maintain the integrity in terms of um, water penetration from the ground up to the ceiling. I mean, the bottom of the joist, and uh, preserves the structural integrity of the building. Okay. Now, nowadays, of course, it varies by region. In California, we are very fond of not using a raised floor system like this one. Okay, for the ground floor. Okay, second floor is mostly wood, always. That didn't change. But nowadays in California, they want to put this a concrete slab for the first floor and wood joist for the second floor. So when you put a slab, obviously you don't have nothing to crawl under, and there's no crawl space. You still have pipes under the slabs, and when there is a leak, it will be very difficult to repair because you need to cut this concrete, break the concrete, open up the concrete, dig, and then fix it, and then pour again concrete. So it becomes more expensive compared to the wood or raised floor system. Also, the raised floor system, you're digging only the footing or foundation, but here you're digging under the slab too because you need to compact that one and put in some gravel base. Um, you also have to still put in this orange thing. It's called the vapor barrier, or a damp barrier system, or non-permeable plastic that stops water from going through, because concrete is porous. It will let water in, it will let moisture up in, it will let vapor in. Okay, so it's important that you put that vapor barrier. And you can see here, here's your concrete slab, and then here's your vapor barrier, and then you have under that one you have your gravel base, and then you have your compacted base, and then the very last one is whatever's in below that, which is your just basically dirt soil. Okay. Here's another section that shows your finished floor. It could be carpet, could be tile, could be wood. Then you got your adhesive or whatever patchy compound. Here's your slab. The concrete is your slab. And after that one, you got your vapor retarder or a vapor barrier. Then you have your sand to make things level because gravel sometimes it's not level. So they tend to put in sand first and water it down and put more sand until it's level before they put in your vapor barrier. Um, and the sand itself tends to be sort of a way for water to build up and then go somewhere else except up. And that's what the vapor retarder is, the vapor barrier. Okay. So because you have water seeping in or vapors coming up from the ground, we have to put a membrane or a vapor barrier called a damp proof membrane all around so that it stops any vapor from rising up. So here's like two kinds of slabs, one that's thickened on the end, uh, not necessarily used for houses, but maybe for sheds, or it could have a thickened end and a separate footing. Uh, and here is another detail where you have your footing and then you have your slab that's separately poured. Here it's monolithically poured, means one pour, you pour the footing and the slab all at once. This one I've seen it done typically more nowadays for houses. They just dig a big trench on the side and pour the concrete and the slab all in one. The problem with this one is it's hard to repair because this is monolithic. It's easy to, I mean, it's not easy, but faster to do because you have the people doing the concrete there all at once. Whereas if you have a slab and footing separate, they have to pour the footing first, let it let it dry, let it cure, come back another day and pour the concrete slab. So this one takes more time to do, which means more expensive because then the guys will have to come back for it. But you can see that there's a membrane here, okay, and it goes all around. And here the membrane only is under the slab, and then there's a connection here. So that's two ways of doing the slab. Slabs are engineered, so the engineer thinks of what happens on concrete is concrete when wet is um, is basically expanded, and after a few days, it'll start to cure, dry up. The moisture is going to be gone, and when the moisture is gone, then the slab will shrink. And if it shrinks, um, the force that makes it shrink will also create cracks. And so the engineer knows this, and in construction, we discuss that in engineering subjects. And if you don't anticipate cracking or take into consideration that shrinkage will crack, then you would see this crack happen wherever they need to happen. And so that's why you're going to see these lines on the floor of concrete. And these lines are control joints or called expansion joints. And they can be done just by making a pressing on it with a tool. So your formwork guy will need to do this control joint, or the guy who pours the concrete when it's a little bit hard uh, to press a tool on it will simply press a metal piece that makes a groove on the concrete. And these control joints will actually um, locate where the cracks will happen. So you're like forcing the concrete to crack at these specific areas or lines. Okay. You could get a saw and cut the concrete, or you could put a material in it, and below that material, it will crack because you weakened that slab. It's not 6 inches anymore or 5 inches anymore. Now it's like 2 inches, and that's where the crack will happen. Okay, so control joint is very, very important. Uh, the least expensive control joint or expansion joint is to um, saw cut that one, put a foam or rubber rod, so to speak, and then cover that opening with a sealant. Another least expensive is to put a rubber expanding gasket inside that. After you cut it or after you remove the formworks, you hammer it down, or some are put in place while the concrete is still wet. Okay. In more sophisticated and more expensive settings like buildings, control joints will be out of two metal pieces with a rubber uh, piece that expands, and when the slab separates, then the metal pieces will go with the slab. Uh, Same thing here. The metal pieces will widen and pull that joint wider, and because it's a more expensive piece that has an integrated fill or rubber cover, then you don't need to worry about how it's going to look. Okay. Now let's talk about slab reinforcement. Slabs are prone to cracking because of shrinkage. Cracks can also appear because it wasn't designed well, and then the loads will basically break that concrete. Okay, and so slabs must be engineered to be strong enough to carry the loads it's supposed to be carrying. And you can either put a welded wire mesh or welded wire fabric. So let's put in fabric here also, welded wire fabric, or mesh, or basically they're just rebars, reinforcement bars that are tied together. So here's a wire mesh. Okay, welded wire mesh or welded wire fabric. They basically made in the factory. They come into like sizes of plywood, and then you basically put them on site and tie the plywood together. Okay, before you put the concrete. Some, the more traditional ones, they have these rebars, and they just get a galvanized wire and tie them together before putting the concrete. Okay. They have the same property, except this one's more convenient. This one's more labor intensive because this one, the welded wire fabric is done in the factory, and then the machine welds them together, and then deliver on site, and then the guys on site will just lay them down on the floor, raise them from the dirt or from the vapor barrier, and then tie together those ends. Whereas this one's very intensive. The rebars will be delivered long. You have to cut them and then put them in place. You have to bend them and then tie each intersection together before pouring the concrete. So yeah, but welded wire fabric mesh is usually not available for like second floor applications like let's say car parking buildings. That one needs to be done with a thicker rebar, and those thick rebars will have to be done individually, so it's more expensive. Okay. Um, so speaking of car parks, the car parks would have to be designed in a way to carry more heavy loads than your typical second floor story for a building or a house, because basically you're carrying cars, right? It's very, very heavy. Multiple cars on the floor, multiple cars driving along that slab. So that slab will need to be detailed in terms of how will the rebars get bent and which one is under which, what thickness is the upper rebar from the lower rebar, and all that other stuff. Okay, because you see here, the lower rebar here is thicker, and then the other direction of the rebar is actually a smaller diameter. Okay, so that one has to be detailed. Sometimes a engineering firm will create a section of the slab and tell you the reinforcement on the slab and what's under the slab and how thick the base of the slabs are. But most of the time, you will see a note on your drawing, and these notes will be sufficient in most cases, and that's what engineering firms usually do nowadays. Okay, so let's look at some of these notes. So, like I have here three notes from the slab on grade notes, and these are going to be relevant to our project. So, note number one, if you look at note number one, it says here that the thickness of the slab will be 5 inches. Yeah, and it says that normal weight concrete. So, normal weight concrete means that a concrete that is filled with gravel, sand will weigh roughly around 2,400 kilograms um, per unit, per square feet, per square meter, whatever, right? This one is a cubic meter, kilogram per cubic meter, right? So this one, that's the weight. Oh, there's ultra lightweight concrete. Ultra lightweight concrete is still concrete, but the aggregates used there are not necessarily gravel anymore, and it could be like styrofoam spheres or styrofoam balls, and basically because they are made of styrofoam, the concrete is very light, and that's where you got your ultra lightweight concrete. Okay, but yeah, and then heavyweight concrete depends on how heavy the stone or aggregate gravel used there, because each type of gravel used is basically one is denser, which is more heavier than the other. Okay, so that's what note number one is saying. Thickness of the slab is 5 inches and it's normal weight concrete. Also, in number one, you would find that the reinforcement is described here as a 6 inch by 6 inch W2.1 by W2.1 WWF. WWF means welded wire fabric. And you can see uh, manufacturers of welded wire fabrics or welded wire mesh would have designations on these, like 6 by 6 W2.1, W2.1. And it's basically a designation for what gauge is the metal used to make the fabric, welded wire fabric, and how heavy, 30 pounds. Okay. Yeah, so that's basically what it means. Um, it would also narrate the what is under the slab. So under the slab, it's 5 inches thick. There's a reinforcement of welded wire fabric, and then under the slab, there's going to be a vapor barrier. So if the engineering firm is like a good firm, they would put this in, because this is actually not their problem. Their problem is engineering and assigning and putting in and defining that there's a um, vapor barrier underneath the slab. That's not their job really. That's the job of the architect, because the engineer's job is about strength. Okay, but like I told you, the architect will have to oversee that, and we say, hey, I want to put a vapor barrier on the slab to prevent water from rising, to prevent argon and methane from rising from the ground. And so the architect would dictate that, and um, the engineer would have to put that on their notes. With some engineers, that's a standard practice. On their notes, they're going to define the thickness, they're going to find the reinforcement, and then they're going to define the vapor barrier must be in between the base of the slab. This one doesn't say that there's sand before the gravel. It only says that there's going to be 6 inch gravel. Okay, thick 6 inch thick layer of gravel, but it doesn't say there's going to be a sand on it. Yeah, so it depends again on the firm. The sand, what its job is to level the surface. So when you put your vapor barrier does not get to be torn up by the sharp edges of the gravel. Okay, so That's basically what note number one tells us. It's pretty much complete, so we don't need to draw anything. Okay, let's look at number two. Number two here says slab on graded mechanical room shall be 6-inch thick. So mechanical rooms, just like a boiler room where you have tanks and heaters that typically sometimes vibrate a lot or is heavy, then the slab on that one or in those rooms will be thicker. Now, I think we do have a mechanical room for the elevator, and that would be the bottom of the elevator pit. So the bottom of the elevator pit is considered a mechanical room, and that mechanical room would have a thicker slab, 6 inches, and everything else is defined, like the vapor barrier and the reinforcement. You can see the reinforcement is different. W 2.9, 2.9, which is a heavier gauge reinforcement. 2.9, 2.9 here is the gauge 6. Okay, so it's a little thicker, stronger, thicker concrete, but basically it has a vapor barrier and some gravel base. Okay, um, the thickness of the concrete adds to the strength of the concrete, but also the mixture of the concrete. So you can see here it says that the it's normal weight concrete, but it is 145 PCF, 3000 PSI, and here's your PSI readings. Uh, Basically, when you're mixing cement, sand, and stone, you create concrete. And the ratio of one bag of cement to one bag of sand and how many bags of stone contributes to the strength of the concrete. So if you want to have a very, very strong concrete, then for 1 part cement, you put in 2 parts of sand, not three, two, and then you also put 2 parts of the stone aggregate, right? One, two, two. Um, Normally 1, 2, 3 or 1, 2, 4 is your normal concrete, okay? But for buildings, they wanted to either use a 3000 psi or 3500 psi, okay? So again, the ratio or mixture of the cement to the sand and to the gravel will also contribute to the strength of the concrete. And last one, let's look at number three. Number three is basically telling us that the elevation of the slab will be at 82 feet 9, datum 00, or from datum 00, whatever. Um, Basically, it tells us that when you pour this concrete, this is going to be this high. Okay, some areas, some big sections are going to be elevated or lower, and that sections that are elevated or lower than the concrete will be marked with an X, and they would be putting in something like negative something or positive something. That means negative is depressed and positive is higher. Okay, so in this case, this one says negative. So this one is 6 inches below everything else. That's what it says. And this one is positive 1 foot 4, so this is elevated above everything else. Okay, so what we're gonna do is we're gonna do this notes like this in AutoCAD, and we're going to make sure that we take care of which slabs are lower than the rest. Okay. Okay, so we're going to go back to our AutoCAD and go to our structural plans where we have our foundations. And let's zoom in here, and we can see that we already have put a mark on the elevator shaft because the floor of this elevator is lower than the floor of our slabs um, for the coffee shop for the um, customer area. Okay, so how low is this shaft? We need to look at the elevators from TKE, the one that we are using. Let me see. Okay, here you go. We have to go to TKE United States website, and on their elevator, we want to click on low rise solution. That's less than 5 stories. And down here, we have different kinds of elevators, and below it, we have elevators for low rise. And because we did not put a mechanical room, the mechanical box will be down um, on the pit. Okay, so we have to choose this Endura MRL, and we click on that one, and it'll tell you information. In particular, you wanted a brochure, or let's say plan your elevator here, uh, and it should give you the pit dimensions. Uh, so we wanted a size maybe like this and that one, and we want just a front. Okay, and then we don't want a fast one, we wanted a speed. And then access your drawings, and look at the PDF file, uh, and open that PDF file, and it should tell us that the pit over here is how deep. So there's going to be a box here for the pit where it has all the necessary modules, electronics, and all that stuff. And on this one, it says that the pit depth is 40. Okay, let me zoom closer. So it says there 4 feet from the finished floor. Okay, it tells you all this other stuff, and then that the mount rail brackets will be 8 inches below each level. Okay, so let's now prepare for a pit depth of 4. Obviously, you can go deeper than 4, uh, but this is the requirement. Okay, so going back to AutoCAD and knowing that this is 4 feet, uh, and 0, 0 is basically on the ground. I mean the ground elevation, and this would be a little bit higher, but maybe just a quarter of an inch. So we're going to designate this finish floor as 0, 0, and therefore this one is -40. So all we're going to do is basically do a leader and point to the intersection here, and simply change, remove my ortho, my O snap, and then basically say that this is -4, whoop, negative whoop, 4 uh, feet and 0 inch. Okay, close the editor. Okay, uh, and then make sure that this one is matching the other structural. Okay, and then I can click on this one and change that, and change the shorten the length of that one, and even bring this closer. There you go. Okay, so that means that this whole section is -40. All right, let's move on to our next one. So as I said before, we don't need to detail a slab. We can typically do that on a notes. So we have general notes here, and we have structural notes. What we could do is we can add another type of note here about the footing and foundation. Okay, so if you look at our document, um, we're going to use this notes here uh, that tells us the thickness of the slab and what kind of reinforcement and what's under the slab. And we have also a mechanical room for the elevator pit that needs to be 1 inch thicker, that is a little bit stronger. And then we have to identify what the slab um, elevation will be. Okay, so let's start with putting in or copying this. And we're going to copy it somewhere here. Let's try to align this. So we're going to move, and we're going to do the insertion and insertion also of this one here. And we're just going to move enter last because it's one on top of the other, and make sure that your ortho is on. And we're just going to put it here. And we're going to change this to slab on grade notes. And we're going to change all of that. Just delete. Okay. And we're going to copy the notes listed here and put that over here. Okay, so we just type that in. You can always put a space here on each note if you prefer. Slab on grade notes, and we should also put in like a line here. And double check what you type for anything that's misspelled or doesn't look right. So slab on grade, unless noted otherwise, shall be 5-inch thick normal weight concrete reinforced with 6x6 W2.1 W2 WWF on 15 mil vapor barrier over 6-inch thick layer of washed gravel. Number 2, note slab on grade at elevator pit shall be 6-inch thick normal weight concrete, 145 PCF, FC is equal to 3000 PSI, reinforced with 6x6 W2.9 by W2.9 WWF on 15 mil vapor barrier over 6-inch thick layer of washed gravel. And number 3, note is top of slab on grade level shall be plus 1/4 inch from datum 00 unless noted otherwise. Okay. All right. So there you have it. That's what you're going to do for the reinforcement of your slab on grade. Not much drawing, just a lot of typing. Okay, so do that for as part of your assignment for this module. Okay.